We'll just start with a quick introduction of me and Jenny, and then we'll start with the presentation. So I'm Shraddha Surana. I'm a data scientist and recently stepped into the global data community lead role. I'm leading the AI ML space at E4R, where we focus mostly on research projects. So I'm currently involved in life sciences projects drug discovery. That's the talk that I gave last time. But prior to that, did some projects in the astrophysics domain, which we will be talking about today. Ujjani, you want to introduce?
Hi, everyone. I'm Ujjani Alam, and I'm a data scientist at E4R. In my past life, I was a cosmologist and astrophysicist for the last 15 years or so. Now I work in E4R, applying data science machine learning in various domains. That includes astrophysics, it includes drug discovery, and also weather prediction models. So today we'll be talking about the astrophysics portion of it. Thank you. Shraddha, you can.
Cool. So I should share my screen. All right. So I hope my screen is visible to everyone. Good. So today's talk is on how we can use machine learning for scientific discoveries. The two talks, projects that we would be going deeper into today are on the astrophysics projects that we are doing. But of course, the concept of it and the methodology could be extended to other domains as well. So in today's agenda, I'll start with just a very brief of what is radio astronomy, because both the projects are in that. And then we would be diving deeper into the prediction of star formation properties of galaxies. This one is a supervised machine learning case study. And then Ujjani will be talking about radio solar imaging, which is an unsupervised machine learning case study. We picked up these two projects specifically because not only are they very different in their domains, but also in the techniques that we are applying to it. Now, I'm a data scientist. I'm not an astrophysicist. So as with anything not being deep into the field, I did think that astronomy is like one field, one area. Only when I got deeper into it did I realize that there are many active areas of research, which includes evolution of stars, nuclear and particle astrophysics, supernova physics, radiative processes, formation and evolution of galaxies, gravitational lensing, and the field is just huge. And from this whole variety, these are the two projects that we took for their good contrast and the amount of value that we would get from them. So to start off with, what is radio astronomy? So this is the frequency spectrum. I think most of you would have come across this sometime or the other. This shows all the frequency spectrum of, I'll use the word light to just mention the whole frequency spectrum, and the visible wavelength is what is visible to us, right? Everything that is visible to humans falls in this visible wavelength range, but wavelengths extend way beyond visible towards the higher frequency and towards the lower frequencies as well. As the frequency increases, we fall into the ultraviolet and X-ray regions, and as the frequency decreases, the wavelength increases, we move more towards the infrared and the radio region. So the radio region is what we are interested in because the visible wavelength, the spectrum is very small. If you look at the whole spectrum, and the radio spectrum is quite huge, and there is a lot of information that is available over there. Also, radio wavelengths travel further compared to, say, X-rays. The Earth's atmosphere absorbs most of the X-rays. So X-ray astronomers mostly place their telescopes in the space. For example, the Chandra X-ray telescope. So on Earth, we have telescopes in the visible region. So for example, TMT, which was one of the talks also that was given earlier, the 30-meter telescope would be one of the largest optical telescopes, measuring wavelengths in the visible region. Right? We are looking at the measurements in the radio wave region. So this was one of my visits to the to a radio telescope site. This is the Westbrook Synthesis Radio Telescope in Netherlands. This tiny person that you see over here is me. And I am still visible because I am standing a lot. The difference between me and the telescope is a lot. So I'm a lot nearer to the camera than the telescope. So I'm still visible. So these were radio telescopes that were spread in a line, which capture wavelengths from the radio frequency, convert them into data, which can then further be utilized. The biggest of these radio telescopes is in China. So they have a natural basin, which they built a radio telescope out of it. Now, the flux values of galaxies or anything else that we are measuring, flux values is basically the intensity of the particular wavelength that falls on this telescope. That is what is measured. And using these flux values in these various radio frequency bands, we can do a lot of analysis on the data. So I just wanted to put this out there as well. While the previous photograph looked like a perfect example of a telescope, this is also a telescope. This is the Astronova radio telescope. And when I visited the site, it took me a minute to grasp it as well. So it's basically like black boxes, but each of the black box has some small antenna in it. And this essentially comes not even up to the knees. So radio telescopes can look very different. So coming to machine learning, right? How does machine learning fit in this whole thing? The typical use cases of machine learning are these. So we have regression models that are used to predict a lot of things, for example, house prices, or to predict redshifts in the astronomy domain. Classifications are used, cat and dog classification is a common example. Clustering is used to group various things together. We have recommendation systems, mostly used in the retail industry to recommend products. We have natural language processing that extracts information from large amounts of textual data. We have computer vision that does a lot of identifying of objects in videos, real time, etc. And machine learning has been successfully used in a lot of astrophysics projects. And the reason why it has become important in astrophysics is because the ability to process the data is not growing with the same pace as the amount of data that is being generated. So we will be getting a lot of data in the future. We want to get insights into this data, make predictions, and create models for various tasks such as classification, regression, clustering, etc. And machine learning is one of the ways that can help us keep up with this data, as it allows us to do things that can dramatically improve the rates of discovery in science. So I'll quickly walk through some of the proven techniques that have been used. So for example, classification of galaxies. So in a database of about 100 million galaxy images, in order to classify into its particular buckets, classification techniques are used. So while this is with 100 million galaxies, recently techniques have also developed where we can classify radio galaxies with very less data. Few-shot learning is used in such cases. And this is how typical radio telescope imaging looks like of a galaxy. Then we have regression. The project that we'll be talking about in detail on predicting star formation properties of galaxies is on regression. They are also used to detect outliers and characterizations. So anomaly detection techniques are used to this because any anomaly that we find would be very interesting to explore further and probably gives us some new information about the galaxies universe. It's also used for source identification if there are certain sources existing, or another project that we would be talking about in more details, the radio solar imaging. So the star formation properties, to give a very quick gist, we are using supervised learning techniques over here. Deep learning is the technique we are using. And in this, while the current model takes 10 minutes per galaxy, which would take like about 2.5 months for millions of galaxies, that's the current simulated model that they have created. And with the deep learning model, we are able to do that in seconds for millions of galaxies. So this essentially accelerates our understanding of galaxy evolution and hence the universe. So it expedites the whole discovery process. On the other hand, radio solar imaging is more about the images of our sun in the radio frequency domain. And it falls more into the unknown realm because we are not very sure what we are looking for. We used unsupervised machine learning techniques in this. And the main idea is to discover patterns and structures in the data set. So focusing on the predicting star formation properties of galaxies using deep learning, I want to start with this image that shows a lot of I can't even call it stars because most of the bright points that you see would actually be galaxies, but they're just so further away, they're seen as points. So even in a small area of the sky, it is called as a survey, there are millions of galaxies which are present. Some of them are visible in the visible frequency, visible spectrum, but a lot more would be seen in the radio frequency spectrum. So we want to study these galaxies and their properties. And in this work, what we have done is we are training a deep learning model to predict some of the basic parameters that are used to categorize the star formation process in galaxies. So these are the current star formation rate, that is the rate at which new stars are formed in the galaxy. The dust luminosity, which is the luminosity coming from dust which is present in the galaxy. The stellar mass, which is basically what mass of the galaxy is contributed by the stars in the galaxy. So it is a rough proxy for the integrated star formation in a galaxy throughout its history. Galaxies have other properties too, such as hot temperature, cold temperature, etc. But these are the three basic properties and main properties of a galaxy that we wanted to start off modeling. So understanding the star formation properties of galaxies is a critical exercise in the studies of galaxy evolution. And there are existing models such as the stellar population synthesis, which are used to figure out some of the above mentioned activities from the flux emitted from the galaxies. So MACFIS is the current model that does this. It is one of the most widely used spectral energy density fitting codes. That's what it is called, and which has been successfully applied on galaxy samples to predict these three properties: star formation rate, dust luminosity, and stellar mass. What this consists of is many templates, and it's more of a brute force method. So pictorially, if I have to show you, this is what it looks like. Each particular dot that you see is the flux measurement. Okay, so each of these is the measurements that the telescope has been able, flux measurement that the telescope has measured. And the green line is basically the template. So there are millions of such templates. And currently what is done is each of these templates are basically mapped onto these points to see which of them fit the best. And whichever template fits the best, that template is taken, and then the properties of star formation, stellar mass, dust luminosity are then extrapolated from this template and estimated. So these SPS models are physically very well motivated, and they encapsulate a vast and growing literature, which provide us with very sophisticated models. However, the complexity and sophistication of such modeling does come at a price, because finding the best model within this vast parameter space, it consists of millions of possible models, as I had mentioned, is a very compute intensive process. And that's why a machine learning approach leaves the building of this complex nonlinear model to a machine learning algorithm to study the data and create a suitable model. This is where we use deep learning to reproduce the capabilities of this stellar population synthesis model. So basically we have these estimates from the SPS model, and we are using these estimates to understand the modeling, the nonlinear modeling that is happening. And we create a deep learning model to be able to estimate these parameters. So deep learning networks generally perform very well in capturing the non-linearity of the data. And they have been successfully applied in various astronomy classification problems, usually, such as classifying into stars, galaxy, quasars. In this work, we are looking at deep learning to apply it in a regression problem statement, that is to predict a particular property and not classify it. So I shall start with the data, because to apply any deep learning model, we do require data. The data we use for this is the gamma spectroscopic survey, which consists of approximately 300,000 galaxies. What this includes are the flux values of up to 21 broadband filter for about 120 galaxies for the survey that we chose. Now, these broadband filters include the far ultraviolet, near ultraviolet, the 5 slow and digital sky survey bands, near infrared bands, mid infrared bands, and the 5 Herschel bands. Along with this, we also use spectroscopic redshift for our prediction. So we cannot use all the data that is present because it is too varied and each measurement has a noise or error associated with it. We do not want too much noise in our modeling as it may lead to incorrect models. At the same time, if you only look for measurements where there are no or negligible errors associated with it, we will have hardly any galaxies to train on. So every time a flux measurement is taken, the possible error associated in its measurement is also noted. So if you think of it in a tabular form, we have these 21 flux values, and along with the 21 flux values, we also have 21 errors that may be associated with each of those flux values. Okay. So what we want to do is we calculate the signal to noise ratio, but even before we do that, we do a selection of samples from our whole data set, which basically means filtering on various parameters. One such parameter that we chose was that the stellar mass should be greater than 10⁹ times the solar mass. Now this encapsulated more than 95% of the data, and at the same time, it made sure that we are not taking data from regions where the representation of data is very less, and also the chances of it being inaccurate increases. So in order to include as many measurements as possible, we calculated the signal to noise ratio for each of these. And galaxies which had at least 6 flux measurements having a signal to noise ratio of greater than 3 gave us a good trade-off. So we experimented with a couple of values. We of course wanted as many flux measurements to be of a good signal quality. 21 out of 21 would be the ideal case, but that is also impossible. But based on various experiments and also down the line of various parameter tuning of a deep learning model, we realized that out of these 21 flux measurements, even if we have 6 flux measurements, which have a very good signal to noise ratio, we can use that for both our training and prediction purposes. So once this model is in production for the 21 flux measurements that we have, even if 6 out of those have a very good signal quality, we can use it to estimate the parameters that we discussed. So a galaxy is excluded from a sample only if it occupies a sparsely populated region of the parameter space, such as, for example, this, a criteria such as this. Or we also found that there were certain flux measurements that were missing or unreliable. So there were certain negative flux measurements which are physically not possible. So we removed those as well. So by doing this filtering and selection, our final sample set is of about 76,455 galaxies. And these are the galaxies that we give to our deep neural network. A separate model was trained for predicting each of the 3 free parameters of the star formation history. Now, the specifics of each deep neural network would be different, both the architecture and the hyperparameters that were tuned. But overall, they would look similar to this. It would have 21 input layers corresponding to the 21 flux bands plus the spectroscopic redshift. It would have some hidden layers, and the number of nodes in each hidden layer would be different for each of the parameters being predicted. And we would have one final output node, which represents the prediction of each of these free parameters. Now, for our experiment, we split this data into training, validation, and set. The model is trained on the training data. Then this model is validated on the validation set. That is, its error is calculated on the validation set. And this error information is then used to further improve the model. We want the model to generalize well and not overfit the training data. So once the model is, we do this so that it doesn't overfit. And once the model is finalized, it is given to the test data to see how well the model performs on the data that it has never seen before. So this basically gives us a good idea of how well the model will perform in real life scenarios. Now, if we look at the results, so this is a scatter plot. This is showing the results for stellar mass. On the x-axis, we have the actual values of stellar mass for each galaxy. And on the y-axis over here is the stellar mass value predicted by our deep learning model. Similarly, in the lower box, we see this is the error between the actual and the predicted value. So the x-axis is still showing the actual actual value, whereas the y-axis is basically showing the error between the actual and that predicted by the deep learning model. This is basically to get a more zoomed version of what is happening over here. So if we see, there is a 45-degree line, which is basically a black line. In the error, we can see that as this horizontal line. Okay, this line is where the actual and the predicted values are exactly equal. Now, when plotting it, when plotting the actual and predicted values, we get a scatter plot of this sort. And then we have created this dashed line, which is basically the best fit line inside the scatter plot. So we see that for stellar mass, these 45-degree line and the best fit line coincide very well. That means overall, the deep learning model is able to predict values very close to that of those estimated by the MACFIS model. Because remember over here, it's the values predicted by the MACFIS model that we are using for our supervised training in deep learning. A few other things which are important to note is that this prediction is happening over 3 orders of magnitude. It's in the logarithmic scale. And we are able to estimate within 0.06 of the actual value of stellar mass. So another caveat, in regions of parameter space where MACFIS is a poor model of the underlying physical reality, our deep learning model will also be a poor representation of the physical reality, because again, we are trying to model the MACFIS model. We can never have like the actual values of stellar mass and the star formation rates of galaxies. So these have been modeled, and it's the output of these models that we are using for training purpose, for a modeling. Similar are the plots for both dust luminosity and star formation rate. For star formation rate, the error is within 0.16. We see that there is a little more scatter around the line. It's not as close to the 45-degree line as was stellar mass. And for dust luminosity, the error is within 0.01. Again, these range from several order of magnitudes because these are in logarithmic scales. So the challenges that we see over here is the main thing was to be able to predict this for as many galaxies as possible. We wanted to do as much as we can to not throw out galaxies that have been measured, and for any measurements that have been taken to be able to predict these star formation parameters. And hence we are able to use galaxies which also have very low signal to noise ratio. So as long as 6 bands have good quality measurements in the whole 21 bands, it was good. This of course took a lot of to and fro in the architecture, hyperparameter tuning, and figuring out how many of these galaxies we can actually use which have very low signal to noise ratio. Also, so these parameters, they are sort of interlinked. The star formation parameter, if it falls between a certain range, the stellar mass would also likely fall between a certain range. So our initial idea was to try to create a single architecture that is able to predict all the 3 and sort of make use of the dependency between these. However, after several tries, we realized that this is not the case. Still predicting them as separate is the best way to go forward, because that gives better estimates. There could be several theories around it. We haven't been able to concretize any of them, but it could be that parameters that matter, so the input flux values that matter a lot to predicting one of the parameters may not matter so much to predicting some of the other parameters. It is just a theory. We haven't gone deep into it. But sometimes, even though parameters may be interlinked, it is better still to have separate models for them. So to conclude, we definitely got a huge savings in time using the MACFIS model, which takes about 10 minutes per galaxy to give output for each of the 3 parameters, which basically means 2.5 months for millions of galaxies. Now we get the same estimates, which are very similar to that of MACFIS model within a few seconds. So most of the learning, most of the time taken is during the training process. So the deep learning technique that we outlined takes about 3 minutes to 30 minutes. So to train some of the models that took only 3 minutes, to train one of the model, which is the star formation rate, that took about 30 minutes. And once it is trained, it can predict these parameters for galaxies, for millions of galaxies in seconds. So this represents a huge savings in time, and definitely larger savings for samples from future large area imaging surveys. This model has a good noise tolerance. Again, because we need only 6 good signal to noise ratio in fluxes, not in all 21. And this would help in accelerating our understanding of the galaxy evolution and hence the universe. So one of the things that we do want to do in future is look at the anomalous results which are there in the plot. So for example, if I show this, there are some galaxies where the deep learning model prediction is very far from the actual star formation rate, which has been estimated by the MECFIS model. So what we want to do is also give some confidence level for each of these predictions, and those galaxies whose free parameters the model predicts with very low confidence, these can then be further investigated and then redone with the standard stellar population technique. So then this outcome can then be further investigated and changes can be incorporated in the deep learning model, or it may lead to some insight into the underlying MECFIS model itself, right? And would help enriching either of the two models. So in this project, we use the spectroscopic redshift. The next step for us is to use the photometric redshift jointly with the star formation properties. Now, one of the things is that the data has to have information in it to be able to predict these values. And even in predicting the star formation properties, we tried a lot of combinations of architectures, hyperparameters, so that the model will generalize well on the data. We do not want it to overfit or to underfit. Now, doing this with the photometric redshift does multiply the challenge, because we use redshift as one of the inputs to our models. Now, if we are predicting photometric redshift, there would be some errors associated with it. And if we are using this as input to predict the star formation rates, the star formation properties, so this error would also propagate. So the error propagation has to be dealt with. So it does get more challenging, but it does get as interesting as it gets challenging. These work led to some publications. I had the good fortune to talk in the ADAS conference, which is the Astronomical Data Analysis and Software Systems Conference, on how machine learning can be used in scientific discoveries in the context of astronomy. The paper is published in the conference proceedings. This is not available online yet, so it is there on archive in the meantime if you're interested in knowing more around this. The prediction of star formation properties of galaxies using deep learning has been published in the monthly notices of the Royal Astronomical Society. It is one of the leading journals in this domain. So if you want to know further details of the exact architecture, what we have done, how we've gone about it, more on the results and its analysis, it would be available in this paper. This paper should now be freely available. It was published last year, and I think after a year, they open up access freely to all. Also, Insights article blog has been published on the same, which is a less technical version of the paper, but incorporates the gist. I'll take a quick pause over here for any questions we have so far, and Ujjani will then pick it up to talk about radio solar imaging.
If you would like to share your questions, please add them into the chat. We haven't received any yet so far.
Either I was too clear or not clear at all.
I see a question just came in. I can read that out from Ian. On the signal to noise ratio, how did you arrive at the final approach?
Was this by trying multiple runs? Yes. So we tried various combinations. We started with a higher number, of course. I don't remember the exact number because this was done 2 years ago. But we started with like at least above 15 should be good quality signals, because that will lead to good modeling. The more noise that is there in the data, the more difficult it will be for the model to generalize. So we started with that, but we realized that the number of galaxies that we would have for our training would reduce a lot. So we kept decreasing it till we got a good trade-off between how many galaxies we can include in a modeling, and of course, when the actual prediction has to be done in real scenario as well, and good quality model. Do you retain the models or refine parameters often? Retrain. Yes, usually we do end up retraining the models a lot and tuning the hyperparameters.
Another question from Ian.
One thing is that we keep retraining based on parameters. Okay. And the other is also based on various combinations of data, because we did put in certain filters in place and we want to make sure they are the best filters. Of course, the values of the filter were also from inputs that we got from from our collaborator, Yogesh Vardekar, who is from NCRA. This work is in collaboration with NCRA Pune, and they are like experts in their fields. So it comes from their experience as well. Right. So was the source data able to distinguish noise versus actual real anomalies? So in this project, we were not looking at distinguishing between the two, but we were more looking at trying to be able to predict these values despite noise in the data. So I hope that's clear. That's where the whole signal to noise analysis came in. Maybe I'll stop sharing. Ujjani, you can start sharing and I can still look at the questions.
Yeah, sure. Okay, so let me know if I should start my portion.
No more questions in the chat so far.
Okay, so I'll start my portion, which is on radio solar imaging. So it is very different from the project that Shraddha just described, because this was an unknown problem. It's a problem where not only do you not know what kind of answer you're expecting, you don't also know what is the question you're asking. So you basically have to define everything as you go along. Why did we pick up this? Was because, there we go, sorry. Why we picked this up is because the images that we have for the sun in radio frequencies have improved in their quality and quantity dramatically over the last decade or so. The Murchison Wide Field Array is a new generation interferometer. It operates in the radio frequency range 70 to 300 megahertz. It can generate up to 100,000 images every minute. Its field of view is very wide. It's 30 degrees across. So you have all this high quality data that is coming our way. And then when SCAR, the Square Kilometer Array, comes about, we will expect another huge jump in the quality and quantity of data that we can have. So we need to find a creative way of using existing algorithms to deal with this huge amount of data. So our initial plan was to just look at this data and try to figure out, with some unsupervised learning techniques, what kind of patterns, etc., we can detect in the data. So here we started out with radio images of the sun in 48 spectral channels over a certain amount of time. Here you can see one snapshot in time of all the 48 images. Here you can see a 4-dimensional representation of the same thing with the time and frequency both represented. And we then tried to classify these images into groups with unsupervised clustering. What we found, given, can people see? Yeah. What we found, given the data that we had, is that the images were divided into frequency bands by any clustering mechanism we used. The time was not terribly important, but all the images were divided into various frequency bands. And this actually points out one of the pitfalls of using unsupervised clustering. it will always find you some pattern in the data. Whether that pattern is something trivial or non-trivial, that is for you to find out. In this case, we found that the images contained so much information that the clustering algorithms were not able to deal with this huge amount of features and just went for the simplest division by frequency bands, which is completely correct, but not very interesting in terms of the science you can get out of it. So if you want to do further work on it, then you need to reduce the number of features you are feeding in to your algorithm. So that then led us to think that we should not look at each and every pixel of all the images. We should look at maybe the peaks that form in the data. And that led us to trying to solve the coronal heating problem. So what is the coronal heating problem? The visible disk of the sun is at 5,800 Kelvin temperature. The solar corona, which is the atmosphere just outside the sun, is at 1,000,000 Kelvin. And we don't know why the corona is so very hot when the visible disk is obviously not. This is a long-standing problem. It is something that has been known for a long time, and there's no real good solution to this. A plausible hypothesis came from the nanoflare theory, which says that there are, due to magnetic reconnections inside the sun on the solar surface, you have many tiny nanoflares coming up, and the sum of all those nanoflares is what is making the corona around the sun so very hot. This is an old theory. It was first proposed in 1972, but so far we've not had any clear detection of these nanoflares. And there's two reasons for that. One is that what you think is a nanoflare could also be something else. It could be some sort of chaotic event in the sun. So it is difficult to separate out the nanoflare from other things. And the second is that the current observational tools are not sensitive enough to detect the nanoflares. But we can think about indirect observation, and which is where the WINKs come in. WINKs are weak impulsive narrowband quiet sun emissions. These are small emissions, compact low intensity emissions that are happening all over the sun randomly, and they would happen as a consequence of nanoflares. So if you find the WINKs, that does not prove that the nanoflare theory, but it is strong supporting evidence. Again, this is something that till recently was not detectable. The first detection was last year from the scientists of NCRA. So we came up now with an idea that we would create a pipeline to study the morphology of these WINKs. And this is possible because now we have this high quality radio frequency data from MWA. So from an unknown unknown, we are now approaching a known unknown situation. It's not a very known question though. Even though we found a question we want to ask, we know next to nothing about the WINKs. So we're not very sure what we will see or how to describe it. We just knew that we should start looking for peaks. So I'll describe the steps we went through in going with that. The first thing is you need data that is quiet, because if you have a very bright active region or a radio burst in the sun, it is going to overcome everything around it. It is going to wash out any small intensity bursts that might be happening. So you need a period when the sun was comparatively quiet. There were no active regions or fewer active regions. So we had two particular data sets, one at 132 megahertz, 8,000 images every half second or so. This was the data set from which the first WINKs were detected. So we did want to take a closer look at it, but it did have an active region somewhere near the middle. So we were expecting that anywhere near this active region, you would not be able to find WINKs, but maybe far away from it, we would be able to find these peaks. The second data we had was an unusually quiet period of the sun, over 4 channels, again, 8,000 images every half a second. This had no active regions. So whatever we saw in it, we could expect that not to be an active region or a radio burst, but something that might relate to these quiet sun emissions. Point to note is that we have actually loads of data available. We have up to 13 hours of data available. We started with about 4 minutes of data. After a year, we are now at a place where we are analyzing about 1 hour, a little more than 1 hour worth of data with the pipeline. But this is something that obviously can be and should be scaled up to deal with the huge quantities of data that we have. So we have these things, and one of the first thing we do is to find the radiosolar boundary. So if you look at this picture, then if I was to draw a line here around it, then that would be roughly the radiosolar boundary. We used region-based edge detection techniques, so Bell and then a watershed transform, in order to find the radiosolar boundary. And this is the boundary that we found, this big red line. The circle in the middle is the boundary of the optical sun. So the radio boundary is larger, which means that we have some extra information in this bit, which the optical sun would not be capturing. Whether that information would be useful or not remain to be seen, but at least we capture this information. We then also use this boundary to align all the images. So why do you need to align the images? Is because every time you take a measurement with a telescope, there can be a certain amount of jitter in the telescope itself, and then measurements are taken in sets. So you have a 4-minute set and then you restart again. Every time you're restarting, your telescope could move a little bit. So in one set of images, your sun could be roughly in this region. In another set of images, your sun could be roughly in that region. That is a problem because we want to look at how these peaks are spatiotemporally distributed. So if we say that we see a peak at a point xy at a time t, does this peak reoccur at a time t plus delta t? That can only be said if the images are aligned. Otherwise, the position becomes meaningless. So that is why we use the center of the mass of the radio boundary that we found to align these images in the hope that it would help us understand the space-time distribution of these peaks. Having done that, next you go ahead and detect the peaks. We used a signal to noise ratio of 5 to choose which peaks to keep. And this is what we got for the 2 data sets. The colors represent how many peaks are there at a given point. So the redder the color, the more peaks were found over the entire time in that particular point. So the first thing for the first image is that we know that there was an active region here, and we know that we were not going to find any peaks in that area around the active region. That is not a surprise. What is perhaps slightly surprising is that there is a kind of structure to the distribution of the peaks. The theory for these peaks seems to suggest that there should be no structure to these peaks. They should occur randomly all over the sun. So it is not clear why certain places certainly have a lot more peaks, certain other places do not have so many peaks. This is even clearer in the other data set that we had. That was a quiet sun. There's no active region. There's nothing that could possibly be contaminating these peaks. But the structures, if anything, are even more obvious here. So you can see that there are places where loads of peaks were found. And then there are other places which are practically empty. And we don't have a good reason for that. We don't know why peaks would not be found in these regions, or why more peaks would be found here or here. So this was, again, something that we were not particularly expecting. So we decided to look at what the median image over time for all of these images looks like. And there we found something a bit surprising. Instead of finding noise, if you take the median image if you follow the argument that these peaks occur randomly, they're not persistent peaks, then at any particular point of space and time, you expect it to be mostly noise, and at particular points of time, you have a higher intensity due to the peak occurring. So overall, the median image should be noise, because most of the time it should be noise at each particular pixel. We did find, however, that there are 3 low intensity peaks clearly in the median image. It is not noise. It has this structure due to these persistent peaks which appear to be there at least 50% of the time. And this was a surprise. And this is one of the beauties and frustrations of an unknown problem, that every time you pose a question, you expect a simple answer and you get something that is completely unexpected. And then you have to figure out what it means. So we had these, but and we don't quite know why they're there. They're too low intensity to be the beginning of active regions. And they last for a very long time, not only over the entire 13 hours of data, but at least one of them can be seen in other wavelengths as well. So they are just there. They're very low intensity, compact. They don't grow. They don't become smaller. They exist. It is not clear why, due to some temperature fluctuations in the sun. So that is still something that we don't quite know what is happening there. But this median image then did help us to understand why we had structures in the raw image, as because the raw image is a superposition of the median image and the median subtracted image. If the median image was basically noise, then the raw image and the median subtracted image would be very similar. But because the median image itself has structure, that structure gets put onto the raw image. And that is why, so for example, in the median subtracted image, you find a peak over here in the corner. That image, when superposed with these peaks, which are already there, could very well end up somewhere completely else. So that explains why, to some extent, why we have the structures that we see. And therefore, we decided to look at the median subtracted image for the peak distribution. What we find here is that the median subtracted image, the peak distribution, is much more what we had initially expected, which was a sort of uniform distribution of peaks all over the sun. That was our expectation, and that is fulfilled. If you want to be really conservative, if you want to make sure that no contamination is there due to the persistent peaks in the median image, then you can just create a mask around those peaks and get rid of the peaks around them, surrounding them, just in case they are somehow being contaminated, and use only the peaks that are left. So that was step one. We found the peaks which we think are good enough for fitting. Okay, then the next step would be fitting. And for that, we tried to take a look at what the contours around each peak looked like. And there we hit another snag, because the expectation was that these are compact objects. And if they're compact objects, then they should be well represented by Gaussians. So you should be able to draw a bounding box around them and fit Gaussians to them, which will give their physical characteristics. What we found is that the different peaks can behave very differently. It's not surprising, but it does mean that you can't use a one-size-fits-all approach. So here you have a nicely isolated peak, and you can imagine, looking at the contours around it, that an ellipse would fit really nicely here. Okay, so you can fit a nice Gaussian. Here you have a peak which is kind of semi-isolated. So if you imagined a bounding box about this size, then you could fit a pretty nice ellipse. If you imagine a bounding box that is larger, then the distortions come in due to the other peaks. And so you could very well end up fitting an ellipse which is very different. So the distortions would then change your results. You also have peaks that are like this, where two peaks are so close together as to basically form a bimodal distribution. And then on top of that, you have distortion from nearby peaks. So these are just 3 examples from a random image that I've picked up. We have about 8,000 images. We have about 20,000 peaks that are above 5 SNR. And you can have many different types of peaks at different angles. So we cannot blindly put a size of bounding box and fit the Gaussians to these. What we tried, frankly, and it didn't work, because like I said, we had 20,000 peaks, and at some point trying to fit Gaussians for a particular frequency, we managed to fit 300 peaks. The rest just wouldn't fit. So 300 peaks is nothing. You cannot do any sort of statistics on them. It's not even one peak per image. So we needed to figure out how to deal with these peaks. Of course, you can go in, look at each individual peak and figure out what an optimal window size is for each individual peak. That's not something that you can do with large amounts of data. Already with 8,000 images, 4 frequencies, it's hard. If you wanted to scale it up to 13 hours of data, so maybe 100,000 images, there's no way that you can go in and find optimal windows for each and every peak separately. But if you don't find an optimal window, then you're not going to fit well. So this is the point, again, where we ended up using unsupervised clustering. So we used dbScan plus TSNE, where we tried to find out, given the peak characteristics, so each peak, we could define some characteristics. What is the intensity of the peak? What is the importance of that peak compared to its surrounding? What is the nearest neighbor? What is, if you draw a contour, what is the largest complete contour you can draw around it? So you take all these characteristics and then you try to divide the peaks into groups. The nice thing about using dbScan is that you don't have to define the number of clusters you want. It will find that by itself, because we don't know how many types there are. So we can't specifically say this is the number of clusters we want, but dbScan will find that by itself. And the TSNE essentially takes all the characteristics and creates a nonlinear function out of them on which the dbScan can do the clustering. We found that for a particular frequency, it found 8 clusters for all the peaks that were found. If you look at any particular parameters of the peaks, then it is not clear what the clusters were formed on. You can see here all the colors are sort of kind of merging together. But here you can see in the nonlinear function of the variables that TSNE creates, it is clear that there are separate clusters here. One other thing we did check was that these clusters are not created on some trivial parameter, like on position. So you get what happened to us with the initial thing, that the clusters were being formed on frequency bands, right? So we didn't want it to say, create clusters based on the position. So everything in the first quadrant goes into one cluster, everything in the second quadrant goes into another cluster. We wanted to check that that was not happening. But here we did see that no, all the clusters were being formed on the characteristics of the peaks themselves and not some non-trivial issue like time or position, etc. So when we have these clusters, how does this help us? Well, now, first of all, looking at the properties in mean average properties in each cluster, we are able to separate the isolated and semi-isolated peaks from the noise peaks or clustered peaks. So about 2/3 of the peaks were isolated or semi-isolated. So we can already predict that these are the ones that are going to be fit well with Gaussians. And the ones that are very, very clustered, all close together, will be just too deformed to be fit with Gaussians. Secondly, and very importantly, it defines what is the optimal window for Gaussian fitting. So instead of creating an optimal window for each of the 20,000 peaks you have, you're creating 8 optimal windows for each of the clusters, and then using those windows for all of the peaks found in that cluster. This saves time. Naturally, you're only creating 8 windows instead of 20,000, but it also gives more accurate fits. So we found 20,000 peaks, and I had said that when we were not doing clustering, we were doing a one-size-fits-all thing, we were able to fit some 300 peaks or so. With this technique, we were able to fit about 13,000 of the peaks pretty well. So it makes the pipeline efficient and automated. You don't have to go in at each individual peak and try to figure out what kind of window you would define for it. It also makes it more accurate and suitable for the large data sets that we have. So this is a picture of what the residuals to the fits look like after the clustering has been done. So the maximum residual that you can see is about 10%, and that too is at the edges where other peaks are beginning to come in. And for the region near the actual peak, the residuals are pretty low. And this gives us confidence for both the peaks that we have, the isolated peaks. This gives us confidence that the fit is good. For the clustered peaks, we know that the fit is typically not going to be good, but at least for the isolated peaks, we are able to do this level of fitting. Okay, so now I'll take a moment to describe what the pipeline for the peak detection and fitting looks like. When we started out, we had this very simple image in our heads that you have the raw image, you find peaks in it at some 5 signal to noise ratio, then you fit them with Gaussians, and you have the characteristics of the peaks, which will give us the morphology of the wings. As you can see, the current pipeline is a little more complex than that. So but at the end of it, we are able to get something that we have confidence in. So what the pipeline now looks like is as follows. You start with the raw image, and then you align the images using edge detection techniques. This is important because then you would be able to calculate things like the median image, which you would not be able to do without aligning. Then with these aligned images, you look at what the contours look like. You find the characteristics for each peak. You put them into a clustering algorithm, which is able to divide the peaks into different groups and define optimal windows for each group, as well as predict which are the groups that are going to be fit well. You then let it create Gaussian fits, check that the residuals are low, take the peaks that have low residuals. And then you have a little thing happening here, a little backflow, which is that from the aligned image, you also calculate the median image, subtract it from the raw image. Then with the median subtracted image, you go through exactly the same process as you did with the raw image. You do the contour fitting, you find the characteristics of the peaks, you use them to create clusters for the peaks, you find optimal windows for those peaks, you allow the Gaussian fitting to happen on these groups of peaks, and you get a set of peaks that are high confidence. And then by comparing what you get from the median subtracted image and what you get from the raw image, you are able to then create a set of consistent fits that we believe represent the true state of the sun, rather than some superposition of persistent peaks in the median image, etc., plus the true peak. But we believe that what we will get at the end of this would be representing the true state of these peaks. And then finally, you are able to get to the answer of what is the shape of the wings. So this is the results that we have for the morphology of the peaks. For the data with one active region, a single active region, these are the intensity, area, axial ratio, major axis. For the quiet sun, these are the same things, intensity, area, axial ratio, and major axis. So we find that mostly they are low intensity. More high intensity peaks are found in the quiet sun data, a median of 231, whereas here you have a median of 124. So that could be because we are throwing away part of the data that is around the active region, and that could have an effect on it. Mostly these are fairly compact, area of 34 here, 24 here, a major axis of 4.3 and a major axis of 3.7 here. The axial ratio between the major and minor axes is 1.7. So in all of these results, these are pretty much to our expectation. These are low intensity peaks, these are compact peaks, as the wings should be. And we are pretty confident, given the state of the pipeline, that whatever data we are quoting here is not due to contamination due to any other processes in the sun, but it is the true state of these solar peaks. So I'll take a moment to just talk about what the technical challenges were for this project. So the first technical challenge was actually in the visualization of the data, because you have 4 dimensions here, 2 dimensions of position, 1 of time, and 1 of frequency. So we had to first figure out what is the best way to represent the data visually. We used ParaView, we used Sandance. You saw one of the representations in one of the earlier slides. So to get an idea of how the data looked. Then we come to, of course, the biggest problem, which is the size of the data. We had 13 hours of data and 48 frequency channels available to us. We started with 4 minutes of data and one single frequency channel. We are now at a place where we are looking at roughly 1 hour of data and 4 frequency channels. And this, of course, can be scaled up to more time and more frequency channels. Now, the techniques we were using to deal with the size problem was when we were trying to use spatiotemporal dbScan kind of techniques, we created multi-threaded codes that would use GPU, that would use PyTorch, in order to make the whole process faster and also to be able to have enough memory to save all this data. That was from the data engineering aspect of it. From the data science aspect, we found some interesting ways to deal with the size of the data. The first was that we reduced the features from the 10,000 pixels of each image to a few pixels per image, which were surrounding the peaks of the images. This immediately gave us a huge boost because without doing this, if you try to do unsupervised clustering, the number of features are far too great for the unsupervised clustering to work. The second thing is that the clustering algorithm itself was used to reduce analysis time, because instead of creating 20,000 optimal windows, you're creating 8 optimal windows. So that saves time. And that again would come in handy when instead of 20,000 peaks, you would have 200,000 peaks when you scale up the data. Then another major challenge we had for this data, this work, was the unknown nature of the problem. Since we knew so little about these winks or nanoflares, since we knew very little what to expect, we kept running into problems one after the other that we were not anticipating. One nice way of dealing with things was the approach that we used to unsupervised clustering. So instead of using unsupervised clustering directly on the images, we used the unsupervised clustering on the peaks and their characteristics in order to divide them, sort of classify them into different types of peaks. This was one of the major reasons the pipeline actually works now. The second was that the image processing techniques came in very handy to do the alignment of the images. If we did not do the alignment, we would not be able to get the median images and the median subtracted images. So the level of confidence that we have on the results now, we would not be able to have, because there would always be the thought that, is there some underlying structure that we are missing? Now we are taking care of that underlying structure. And also an understanding of how these underlying structures would convolve with the actual structures around the wings. So we had to use various statistics to ensure that we are getting the correct results. So these were some of the technical challenges and how we dealt with them. In conclusion, this algorithm in its current form successfully identifies and is able to characterize the shapes of isolated wings. It can identify the clustered emissions, but it cannot really characterize the shapes. Wings are found, as expected, to be randomly distributed in space and time. And also the size and shape of the best fit Gaussians is very consistent with our expectation of the wings being compact, low intensity features. Some surprises were thrown up, like the persistent features that are very low intensity. But overall, the subset of peaks that we are currently dealing with, we feel give off the right values for these wings. Edge detection and alignment had allowed us to do the consistency checks for the Gaussian peak fitting, and the unsupervised clustering increased both the accuracy and the efficiency of the pipeline. So in future work, one very important thing to note is that we are at the moment using the frequency channels separately. And we are also using only 4 frequency channels. So it is, of course, important to use all the data that is available to us. So we expect to be able to use this pipeline on the 4-dimensional space, X, Y, time, and frequency, and be able to understand the distribution of these peaks in frequency as well as in time. We have explored the distribution in time. We have not really explored the distribution in frequency. And also we could extend this to look at solar emission structures that are not just these winks, but other different types of solar emissions or bursts, and try to classify them. So we have one paper out in the archives, which is from the ADAS conference proceedings. And we are now in the process of doing another paper, creating another paper, which should have a lot of details about how we did this work and what the results are. So with that, I'll give over to Shraddha, I think, to conclude. Shraddha, I think it's better if you share the screen for this.
Sure. Okay, so to conclude both the projects that we have seen, they had classical techniques, traditional techniques that help do the same thing. And we are looking at how we can use machine learning for these. So we do see some novelty in it, while typical research involves using certain techniques and going in a direction which is more based on the experts in the field and their experiences. So for example, using the unsupervised techniques that we used in radio solar imaging, we look at it as a tool that can be used to show different directions that are possible in a project, different things to look at. Feasibility wise, so when considering the number of dimensions and features that are present in the data, it can become infeasible to wrap one's head around everything, the information that is present in the data. For example, if we look at the radio solar imaging itself, so it's basically pixels in the image. So we have like positional information over there. We have information based on time. We have information based on frequency, and the actual flux values which are there. There could be other information like polarization or non-electromagnetic parameters. So there are a lot of things that are going around, and it's difficult to look at everything at the same time. So again, we hope that by using unsupervised machine learning techniques, if any of these are evident, it helps bring that out and sort of give a direction that could be looked into further. Definitely, it is faster over classical techniques, as we saw in the first project of predicting star formation properties of galaxies. Once it has been trained, the deep learning model can estimate these parameters with a good precision for a large number of galaxies in a comparatively very, very short time. So it becomes more scalable and extensible. Especially this is important because astronomical data sets have grown exponentially in size, and the number of astronomers have not increased proportionately, right? So there's lots of information that is being collected. There's lots of information packed in the collected data that can be explored. And the information that is being collected is of an area that we have some information on, but there is a lot more to uncover out there in the universe, right? So right from the amount of data which is there, being able to extract even the small hints of information that may be there in the data, all of this makes use of techniques like machine learning quite inevitable. Also, so there are many telescopes which are present, right? And SCAR is the new telescope which is coming up. And the amount of data is going to increase by orders of magnitude. It is impossible to scale the number of people analyzing, looking at the data in the same manner. Just to give an example, the Large Hadron Collider experiments produce about 90 petabytes of data per year, and maybe an additional 25 petabytes of data produced per year from experiments and data other than the main one. With the new SCAR telescope, which is a square kilometer array telescope, which would be coming up, the rate that data would be produced is approximately 0.5 to 1 terabytes per second. So we need techniques that would scale up to that level. And hopefully we have just started with these two projects. That's all. Thank you for your time. Hope you found it interesting. Any questions?
Thanks so much to you, Jenny and Shraddha. Yes, please, if you have questions, write them in the chat. And while we have some.
So yes, was TSNE used for visualization of the clusters or as a dimensionality reduction method? In this case, we did use it as a dimensionality reduction method. It is usually used for visualization, but you can also use it for dimension reduction. And we found that if we we did this dimensionality reduction, that did help with the clustering. So it's pre-processing before we applied the DBScan. Okay, very interesting, thanks. Are there constraints on where unsupervised learning can be used in a scientific setting, especially in terms of being able to explain how results were arrived at? So there's no constraint on using the methods, right? You can apply the methods to anything. Whether that will give you something that is defensible is a different matter. So we showed you an example of where it is just dividing things into frequency bands, and that is correct, but uninteresting. You could also have a result where it's a bit like a black box. It has found you some result, and now you don't know what it means, because ultimately you have to make the connection to physics. You have to make the connection to the true universe. So you can't just, you can show a figure saying, oh, it's gone into these clusters. But if you don't have a good physical reason that you can come up with, then it won't make much sense. So that's a pitfall. You need to be able to analyze the result properly.
Yeah, in most cases, unsupervised learning is used mostly for grouping clustering. These are then further given to other modeling techniques as well, but it usually involves, once these clusters are created, to go look at these clusters and see if there are any identifiable differences. They're also used a lot for labeling. So if you have unlabeled data and you want to be able to predict a predictive or classification model for it, one of the techniques is to manually label it. So for example, Galaxy Zoo was where they just had all these galaxies out and people actually labeled it, and then they used a supervised learning technique on it. But the other way could be like semi-labeled, where you label some of them, and then you have like huge unlabeled data that is impossible to like manually label if there are like millions and billions. Then a good idea would be to use a clustering technique, unsupervised learning technique, to group these, and hopefully some of these labels fall into the groups separately that can help us label the data.
So that also carries the pitfall that if the clustering has done the labeling a bit wrongly, you don't get to know that till a long time later, because then you have the manual labeling, then you have the supervised clustering, supervised methods applied to it. And then maybe if your results don't make sense, you go back and check what the unsupervised clustering did. So yeah, it's a very powerful method, but it comes with its problems. Were autoencoders considered for dimension? In this case, no. We did feel that we knew so little about the data that we really did not, when we did the feature reduction, we did want some physics behind it. And the physics behind it in this case was that we were considering the peaks, that we understand that there are peaks. So we did not want the dimensionality reduction to increase our uncertainty in the method. So in this case, the dimensionality reduction was done from the point of view that we know some physics that is going into it.
Wonderful. Well, we're waiting to see if more questions come in the chat. I just wanted to remind everyone that we have some upcoming sessions, and the next one will actually be next Thursday on cyber physical systems. So looking forward to seeing you at future events also. We'll ping that information in the chat shortly. All right, if we don't have any more questions, keep them coming in if you have one. I would just say thank you so much to Eugenie and Shraddha for a fantastic talk. And yeah, thanks so much to everyone for joining. And again, as I said, looking forward to seeing you at future sessions.